we feel that we feel really privileged to be part of it and contribute in our own way. So this is one of our contribution, what we can do for history and for the larger society as a whole. So today we will discuss about a topic which is called energy efficiency with low flow high density chiller and chill water system. It's a very interesting topic. Before I get into the depth of it, we will also take you through the basics of chiller a bit, so that I know for many of you this might not be required, those initial slides, because I mean, we all are day-to-day basis, we all are conversant with the the refrigeration cycle and pH diagram. But nevertheless, for the larger audience, just to start with, I will just thought of brushing up these things and then getting into the actual subject. So chiller basics, it is a basically vapor compression cycle, follows a vapor compression cycle, and this is the typical cycle of vapor compression. So from evaporator, the refrigerant goes to the compressor, where refrigerant is basically compressed. So it converts into a high temperature and high pressure refrigerant. Then it goes to the condenser, where it rejects heats and get condensed to the liquid form. And then through expansion valve, again it comes to the evaporator in a form of a air and vapor, liquid and vapor mixture to the evaporator. And this cycle gets repeated. So this is the basic chiller cycle which everyone knows. And I thought of touch basing this pH diagram also. So the same thing which is represented in a diagram form. So this is in a graphical representation of that. I'm not getting into the depth of it because I'm considering that everyone is quite aware of it, because this is the very basics of chiller. Now getting into the different type of compressor which is available. So these are the basic compressor technology which is very common in our industry. So one is reciprocating compressor. Nowadays we have stopped using it because it has been outdated. Earlier we used to use it, but now it has been outdated, and that entire place has been taken by the scroll compressors and helical rotary compressor, which is also famously known as a screw compressor. So obviously the scroll compressor we normally use for a smaller application. Mid-size application is catered by the screw compressor, which is helical rotary. And once you are getting into the bigger application, that is the bigger capacity chillers, obviously we have to switch over to centrifugal compressor. Just to touch base, what are the different type of condenser we have, because based on this type of condenser we designate chiller as water cooled and air cooled. So these are the different type of condenser which is available. So water cooled condenser, as we all know that the refrigerant actually discharges the heat to the cooling condenser water, and obviously it goes to the cooling tower, and that heat get dissipated to the atmosphere. Whereas in case of a air cooled condenser, it directly transfer heats with the ambient air. So this is the basic difference between air cooled and water cooled condenser. A typical range of air cooled and water cooled chiller which is presently available in the industry. So from that chart you can understand that obviously for a smaller application we can still use air cooled chiller, but if it is a very big application, even for a smaller application also we might explore for water cooled chiller. But for bigger application it becomes a mandate, because you don't have air cooled chillers available, because obviously air cooled chillers are, the footprint of air cooled chillers are quite large. So if you go for a very high capacity chillers, so it is very difficult to accommodate. So that's why we had to switch over to water cooled chiller. There are other aspects of it, obviously the efficiency part. I'm not getting into that because that's a separate topic, and maybe some other day we can discuss about it. Basic chill water system for a water cooled chiller. So I have not got into a what is presently being used, but this is a very basic chill water system which is normally being used. A chiller is connecting with chill water pump, from chiller, chill water is going to the cooling coil. From cooling coil, chill water is getting heated up, and through pump it's getting recirculated, and the process gets repeated. On the condenser side, obviously, uh, from the cooling tower, from the cooling tower basin, the cold water is coming, it's absorbing the heat, it's getting heated up, and then again going back to the cooling tower. And uh, this fan is actually discharging that heat to the atmosphere, and the water is further getting cooled down, and this process gets repeated. So it's a again, chill water is a closed loop system, and this process gets continuously repeated for a chill water system. As I mentioned that for air cooled chillers, there is no cooling tower and the condenser water pump which is required, because it directly exchange heat with the ambient air. So you can see the change in the system diagram. So only the chill water circuit, you have a pump which is circulating water through the cooling coil, and obviously the hot water from the cooling coil, the hot water is going to the chiller directly, and this process gets repeated. So now, as you know that the system, I have already shown that what is the chill water system. Now you can understand the various component of it. So because we are going to discuss about the various component and how we can optimize the design in our subsequent slide. So I thought of breaking it down so that you understand that what are the important component we have in a chill water system. So these are the important component what we have in the chill water system, and obviously we will discuss in detail in the subsequent slide about this. Okay, so this is a basically for normally in HRI condition, this is a typical condition for selection of a chiller. I mean, you can consider this as a thumb rule, because I mean 90% cases we select chiller based on this configuration. This is obviously at a HRI condition. We are discussing. We will discuss today about HRI condition only, because I'm just taking it as a basic condition to discuss about the concepts. Obviously, uh, we don't select chiller in HRI condition, because obviously our Indian condition is different from HRI condition. So, but the concept remains same. So just to discuss the concept, I have taken a generic terminology which is HRI condition. So what HRI condition says that the flow rate of evaporator and condenser should be 2.4 GPM and 3 GPM, whereas your chill water out temperature is around 44 degree, which is around 6.67 degree, and condenser water in is around 85 degree Fahrenheit, which is around 29.44 degrees centigrade. And obviously there is some kind of recommendation for the fouling factor of the heat exchangers. So we have two heat exchangers in chiller. One is your cooler and other one is your condenser. So HRA recommends this fouling factor to be considered. If we take air cooled, similarly your condenser circuit gets eliminated, so it directly exchanges the heat. So this is the typical HRI condition for selection of a air cooled chiller. Same 2.4 GPM and 44 degree Fahrenheit chill water out, whereas air over condenser, this is an ambient temperature actually, which we call as a air over condenser temperature. This is to be considered at 95 degree Fahrenheit, and your fouling factor remains same as you have seen for the water cooled, for the chill water side. So coming back to the basic load formula, this is very important, because I mean all our discussion will be based on this. So I request you to focus on this formula. So this is nothing, it's a very basic formula for a capacity calculation. Q is equal to mcp delta T, where m is basically nothing but the you can consider as a mass flow rate. So in this case, like if you are your medium is water, so it's a fluid flow rate of water. Specific gravity of water is basically, you can consider it as one normal cases, and delta T is basically the temperature difference between chill water in and out. So if these are the component, your total capacity or the total load can be calculated by this formula. So it is calculated by this formula. So load BTU per hour is equal to flow in USGPM into degree Fahrenheit in and degree Fahrenheit out. This degree Fahrenheit in and out is chill water in and out temperature into 500. Now, as we all know that 12,000 BTU per hour is equal to 1 ton. So if you want to know the tonnage, you have to divide this by 12,000. So this formula will come at flow into delta T divided by 24. So this is how the formula is being calculated. Again, few chiller terminology which I think we use quite frequently when we discuss about chiller. So I thought of just touch base on that. So IKW per TR, which is very important to know, because when we talk about a chiller, always we talk about kilowatt per ton. So kilowatt per ton, it is nothing but this total electrical kilowatt consumption divided by the total capacity delivered in TR. The same thing we represent as a coefficient of efficiency also, coefficient of performance also, which is called COP. So COP formula is, you can derive from kilowatt per ton if it is given. So automatically 3.516 divided by kilowatt per ton, you can get the COP. Sometimes this efficiency terminology is also represented in EER form, which is called energy efficiency ratio in BTU per watt hour. So it is all the same dimensional analysis basically. So again, 12 divided by IKW per TR, you can get that energy efficiency ratio in BTU per watt hour form. NPLV and IPLV, these are the very common terms we use for any chiller selection. So NPLV, the full form is non-standard part load value, and IPLV is integrated part load value. It is basically the average power consumption of a chiller, because when we talk about IKW per TR, normally we talk about at full load, which is called 100% load. But there is an assumption that chiller will always not run at 100% load, because as you know that in any building, the load profile will vary. So the chiller will also run sometimes in the 100% load, sometimes in partial loads. And there is an assumption to calculate the IPLV and NPLV that 1% of the time the chiller will run at 100% load, 42% of the time the chiller will run at 75% load, 45% of the time the chiller will run at 50% load, and 12% time the chiller will run at 25% load. So now you calculate the weighted average of these 4 parameters and you get the NPLV or IPLV. IPLV is basically calculated at a HRI condition, whereas NPLV is calculated as a design condition. So this is basically the weighted average of these 4 conditions, kilowatt efficient average efficiency of these 4 different tonnage. So just to give you some kind of idea, I mean, what I was explaining, it is in a little graphical form. So this is how the IPLV is being determined, and it is considered that 57% time the chiller will operate at either 50% or 12% load. Again, this is an assumption. There is no need that in any case, in any building, your chiller load profile or chiller running hours will be according to that, because this is some assumption which is made, and based on that IPLV and NPLV is calculated. It is just to create a benchmark to compare the efficiency level of various chiller. That's it. And if you get into the depth of it, you will find that it says that this for C and D, the kilowatt per ton at 50% load is basically considered at 65 degree Fahrenheit, and also this D, which is 25% load, is also calculated at 65 degree Fahrenheit. So you can understand that most of the time it says that 50% of the time the chiller should run at 65 degree Fahrenheit condenser in temperature. Now, who are the system designer, we all know that this is kind of impossible, because in practical condition, like if we are in Kolkata, we know the Kolkata wet bulb condition, 57% time 65 degree Fahrenheit condenser in temperature is almost impossible. So practically when we actually want to evaluate a chiller efficiency, we actually get into the depth of it. We need to get the building load profile. We need to get the practical weather data, which is available in various platform like ISHRE also provides the hourly data. And from there, we have to actually calculate that what is the percentage load and what will be the corresponding condenser in temperature at which the chiller will operate. And then calculate the actual part load value instead of this IPLV and NPL. Okay. So I have just tried to brush up the basic chiller knowledge so that we can discuss in detail about this low flow high delta T system. And low flow high delta T system is also called Earthwise system as well. So if you see this particular graph, it actually shows the picture of a Earthwise system. And this Earthwise system, this is the kind of energy and environmental message which is introduced by US EPA nearly a couple of decades ago, around 20 years ago. And today it is kind of fundamental part of ASHRAE sustainability message and US Green Building Council lead program. Also, what it says that I mean, with this kind of system, they want all the manufacturers, system designers, system integrators, consultant to focus on a system where you can drive down the emissions. Emissions means we are talking about greenhouse gas emissions. So any kind of emissions to the lowest level and energy efficiency to the highest level. So you need to design your system in such a way, you need to design your product in such a way that the emissions should be minimum and energy efficiency should be at the top, at the highest level. Not only that, I mean, that is not good enough, because whatever you design, that needs to be sustainable also throughout the life of the product or life of the system. So suppose today you introduce a system with very, very high energy efficiency and very, very less emission. Tomorrow this system fails. So that is not an Earthwise system. It has to be designed in such a way that it should be sustainable. And the documented means you need some kind of documentary evidence to prove it also. So you need some kind of BMS or some kind of controls which will continuously monitor this performance and record this performance. So this is in brief about this Earthwise system. So this fundamental will practically affect all the industries, and say for the chiller manufacturers like all the chiller manufacturers like us will continue to focus on product where the emission will be very, very low and efficiency will be very, very high. That's how we should do our value added design for any of the equipment. Obviously, you can understand, as I said, that this performance has to be sustainable. So our service and parts team needs to see that this performance and services has to be sustainable throughout the life of the product. Now, obviously, this is just a beginning. So you all might be very, very curious that how we achieve this Earthwise system. So we will come into that in detail. Just to brief you about various Earthwise system which is available, there are geothermal kind of system which is also called Earthwise. So anything which is beneficial for Earth, that is basically called Earthwise system. And I have already shown you what are the pillars for that design. Heat pumps, obviously that is also an Earthwise system. But in today, actually, I will actually focus on the chill water type system with low flow and low temperature, high efficiency design. Now with this, the question comes that what do this system do and how this system works and why to use that. So these are the three very important questions which I will discuss and answer in the subsequent slides. Yeah, this is what I was just telling, that these are the very three important questions to know before we start using it or before we start adapting to it, this kind of system. So this is little, you can say that little out of the box thinking. I mean, as I progress to the presentation, you can understand that every time I am discussing something like challenging the conventional type of design which is presently available in the industry. So what low flow, low temperature and high efficiency system does, it basically reduces the first cost also. It reduces the operating cost as well. It reduces the HVAC footprint. And at the same time, it increases the comfort, it increases the indoor air quality, and it increases the acoustic performance of the system as well. So this is quite remarkable because I mean, for a system designer, for a chiller manufacturer, everybody is practically eyeing to get this kind of system where your first cost should be less, your operating cost also can be minimized, your HVAC footprint can be minimized, your comfort can be increased, you have a better acoustic performance. So obviously, so how we are able to do that? Let's come to that. So what is there in the core? So the same formula of capacity is coming into the picture. If you see, Q is equal to mass flow rate into delta T, which we discussed in the previous slides. So what it does practically, let me explain. So it practically it reduces the supply at temperature. Now in the previous slide, I have already explained you that as a conventional design, we take the supply at temperature as 44 degree, for chiller out temperature as 44 degree. So what this Earthwise or the low flow high delta T system does is that it reduces the temperature supply temperature. It increases the temperature differentials. That means if you normally see the design condition, you will find that we conventional systems are designed with 10 degree delta T, that is 44-54 chill water in out. Here what we are doing is we are actually challenging that. We are saying that not 44, let us go down on the temperature, let us increase the temperature differential. That means it is saying that you reduce this 44, you increase the delta T. That means 44 and 54, this 10 degree delta T should be increased. And from this formula, you can understand if Q remain constant, if Q is your capacity, if you increase the delta T by this supply, reducing supply at temperature and increasing the temperature differential, that means delta T is increasing. What it means is that it will drive down your flow. So your flow tend to reduce. So when your flow reduces, in any, because our entire system is based on this particular formula. So when your flow reduces, you can downsize your piping, you can downsize your ducting, you can downsize your pump capacity, you can downsize your HU fan capacity as well. So when you are downsizing this particular thing, so obviously your cost benefit is continuously coming. And we will also discuss that how it is also save you your operational cost. So this is basically is the core of this design, to reduce the supply at temperature and increase the temperature differentials. So this is a very important question, like why use LLH system, that is low flow, low temperature and high efficiency system? Because obviously it is good for business. I mean, as I explained, if your first cost is getting reduced and if your operational cost is getting optimized, then that is what we are actually looking for. Environmentally responsible, as I mentioned, it is reducing utility generated greenhouse gas emission and uses less natural resources, because when you are downsizing your equipment, obviously it is consuming less power, it is consuming less capacity, so less refrigerant, less electrical power, so you are using lesser natural resources. And it is ideal for almost every industry. So it's, be it industrial, be it healthcare, institutional, governmental, office, all kind of application you can use it. So that's what I mean by this approach. What we are trying to say is that instead of a normal commodity selling, like a typical conventional approach, what is continuously being sold in the industry, let us do something different and convince customer to see the system efficiency in a different way. So rather than selling some commodity, let us sell a system. Okay, so now we will get into some kind of practical examples of it. So this particular system performance has been seen over few of the, obviously, I mean, we are discussing about something which is introduced in US first, and they have done some kind of research on it, and they have tried this system in various cities, which is actually denoted here with a conventional system. Now, what is conventional system? As I discussed, 10 degree delta T in condenser and chilled water circuit. Instead of that, when they compared the energy consumption of Earthwise system in the same city, in the same system, these are the result. So what is the result in the energy efficiency? Depending upon the various city, obviously it will vary. So there is an opportunity they have seen from 3 to 30%, 7 to 30%. So minimum is this Minneapolis, where they have found that it's only 7%. But obviously the other cities they have seen is close to 20-30% energy savings has been obtained by this particular type of system. So this is how this particular system gained popularity in US and gradually has been implemented. Okay, so we are actually now getting into the details of it, that how to achieve this particular system and why this kind of benefit we are getting. So just to discuss about the chiller efficiency and COP. So what we have seen over a period of last 30 years, chiller efficiency has improved drastically. I mean, you can see this graph where on the left hand side in various years, Ashtray 90.1. So that is basically some kind of benchmark for chiller efficiency. So in 1977, this was the chiller efficiency which was benchmarked by Ashtray. Then 1980, they further improved it. 89, 99, they have improved it. But with respect to that, if you see the best which is available in various segments, this is on the extreme right. So if you see that the chiller efficiency has increased by many fold over a period of last 30 years, and now you can get centrifugal chillers close to around 7 COP, screw chillers above 6 COP. So this gives a lot of benefit to do this kind of experiment in case of a uh, low flow high delta T chiller. How? So this is a very interesting question. Uh, we know that combined efficiency of pump and motor is close to around 70 to 75%. So if you actually represent this in a COP terms, it's close to 0.7. And in an efficient chiller, you can get a chiller COP which is close to 7 also. It is available 6.8, 6.9, 7 COP is chiller is also available. So practically, if you see, the chiller efficiency is almost 10 times than the COP of the pump. So here the conclusion is that you work your most efficient equipment harder. That's what we do, right? In any organization, if you find some best performer, so we give him maximum work so that we get the best output. Even in a cricket team, like say for an Indian cricket team, we depend upon Virat Kohli because he is the best efficient player probably. So this is the same thing available in a system as well. So chiller is having maximum efficiency. So let us put maximum work on the chiller, because then the power consumption can be optimized. Because if you work your non-efficient equipment harder, your power consumption will further go high. Another few data that why people have now started focusing on this your apart from chiller, the other system which is pump, cooling tower and the piping arrangement is because in 1980s, if you see, the chiller power consumption was close to around 73% of the system and 27% was ancillary power consumption. Whereas now if you see, this power consumption has almost become 50-50, if not 50-50, but very close to 50-50. So that's why it is all the more important to focus on the how you can design the system so that the power consumption of ancillaries are also can be reduced. So this is a typical rule of thumb which we normally do a design: 10-degree delta T across evaporator and condenser with 2.4 GPM per ton flow rate in the evaporator side and 3 GPM per ton flow rate on the condenser side. Now, still we promote that. Obviously, 90% of our design is with this. But this is what Ashtray Green Guide is promoting. They are saying, as I already mentioned, that low flow high delta T system means you have to reduce the chill water temperature and you have to increase the delta T. So what they are saying that you increase the delta T to 16 degree across evaporator, 16 degree Fahrenheit and 15 degree Fahrenheit to the condenser by reducing the flow rate to 1.5 GPM and 2 GPM. How this is going to benefit, you can see in the subsequent slides. This is just a brief example of a 500-ton chiller when it is run at 3 GPM per ton condenser water flow and 2 GPM per ton. What is the power consumption difference which is coming, and vis-a-vis what is the power savings you are getting by downsizing the cooling tower and pump. So if you see that though we are reducing the flow rate on the condenser side, and though the chiller power is going little bit up from 269 kilowatt to 285 kilowatt, but the savings what we are getting in the cooling tower as well as in the pumping system, that is enormous, because you're ultimately the overall power consumption is still lesser with 2 GPM per ton. And by this 2 GPM per ton, what you are further achieving is that you are able to downsize your piping, if you downsize your cooling tower, you can downsize your pump. So your first cost can also be reduced. This is an example that obviously you can say that chiller, you are discussing about the 100% load. What will happen in the partial load? Now the partial load, what will happen that because chiller is the maximum portion it takes, and the as per present design, the pumping power saving in the partial load or the cooling tower power savings is not that enormous. Your gap will further increase. So if you practically design this 3 GPM and 2 GPM per ton in the part load, it's also you will get a lot of benefit of the total power of the system. So is the cost part also. As I explained that your condenser water cost will also go down, your tower cost will also go down, the chiller cost will remain same. So overall first cost will also be can be optimized. So what we learned practically is that ancillary equipment can become a dominant energy consumers at part loads, and low flow system design save operating cost at design also and part load also, and low flow system design save fast cost as well. Now we will slowly and gradually get into the design depth of it to understand that how it is being achieved. So we will take this component one by one to find out the impact of it. I have already initially I have shown you that there are various components of a system. In case of a chill water system, it is not only chiller. So we are now gradually going to discuss one by one about the various component sizing and its impact if we are designing with low flow high delta T system. These fundamental laws are very important because the entire low flow high delta T system is dependent on that. So this is basically nothing but the affinity laws, where we know that the mass varies directly in proportion with the flow. Pressure drop is actually varies square of the flow, and energy consumption varies cube of the flow. So this is to be remembered while we discuss all the subsequent slides. So let us see the impact on the cooling tower. So normally, if we design with a 10 degree Fahrenheit delta T and 7 degree approach cooling tower, say this is the condition. 78 is basically the wet bulb temperature, 7 degrees approach. So this cooling tower kilowatt, the fan mode kilowatt is around 32 kilowatt, and the same cooling tower and flow rate is 2400 GPM. Here actually, sorry, I just forgot to mention, we have taken a 800 TR machine, and we are discussing about the typical conventional design 3 GPM per TR. and seeing the impact of the cooling tower. So it's a 800 TR machine, so 3 GPM per ton practically gets into 2400 GPM. 10 degree Fahrenheit is the range, that is the delta T, and 7 degree Fahrenheit is the approach. So with this, the cooling tower power consumption is around 32 kilowatt. Now we are seeing the same thing with 1600 GPM and 15 degree Fahrenheit range. We are increasing the range because we have discussed that this is the high delta T system. So we are increasing the delta T. So what we are seeing that the same cooling tower can deliver this performance with 1600 GPM. So with 1600 GPM and 15 degree Fahrenheit range, your cooling tower total heat rejection remains same. So it is able to cater the 800 TR requirement with 32 degree, same power consumption. But here if you see the flow rate for they got reduced to 1600 GPM. So if your flow rate gets down to 1600 GPM, what will happen? It will have an impact on the pumping power, that is condenser water pumping power. Now to optimize it further, if we say this is a 5 degree Fahrenheit approach design, okay, so normally we design cooling tower with 7 degree approach. Now if we consider 7 degree approach, your condenser water out will go to 100. Condenser water in we are keeping same, wet bulb is same with 7 degree approach. You will find that with 1600 GPM and 7 degree approach, what is happening? You are making this particular cooling tower more efficient because it is range by approach. So basically range by range plus approach. So basically you are making it more efficient and your cooling tower power consumption is basically reduced from 32 kilowatt to 24 kilowatt. So this is an optimization which is possible and it is achievable with a smaller tower also, because as you are increasing the approach, you are going for a higher approach in the cooling tower, your cooling tower size or footprint will be lower along with your flow rate as well. So the lesson learned is basically we have to keep the tower as hot as possible. Okay, so now we will get into the cooling coil. What is the impact of performance of the cooling coil with high delta T? This is a chill water side. 504 MBH is basically close to around 42 ton. It's basically mega BTU per hour. With conventional 10 degree Fahrenheit and 2.4 GPM per ton, with entering water temperature as 44 degree and 54 degree, your flow rate is around 101 GPM with this combination. Now let us see what is available if we increase the delta T to 16 degree. Okay, so with this 16 degree delta T and 1.5 GPM per ton, this is what we are achieving. So your delta T becomes 16 degrees. So what will happen as practically we will reduce this chill water temperature to 41 and your living water temperature will go high up to 57 degree. The remarkable savings which is there, which is at this flow rate, if you see. In the flow rate, you will find close to around 37.5% reduction in the GPM because you have gone for this high delta T system. And as I mentioned, you can see the cascading effect of this lower GPM on the pumping power in the subsequent slide. So same, I'm keeping the example same 800 ton with 2.4 GPM. If you see the chill water pump, GPM will be 1920 GPM. Pumping head is around 110 feet. Let us consider that the full pumping head is around 110 feet. The pump efficiency is 80%, motor efficiency is 95%. With this configuration, the pump power is around 52 kilowatt BKW. Now with this reduction in the flow rate, what we have done is that we have calculated with 1.5 GPM per ton. So 1200 GPM, you see the effect on the pump head and with the pump power. Now why this effect? Because affinity law says that the pressure drop varies square of the flow and power varies cube of the flow. So practically what you are seeing is when you are reducing this flow rate by 37.5%, your power consumption reduce in the cube of that. So that's a huge savings. It's close to around 70% reduction in the pumping energy consumption. So what we learn is that the chill water should be cold as possible in the high delta T system. Now, obviously, we have to do away something. We cannot get everything, all the benefits. So what is the effect on the chiller? Yes, because when you are reducing the chill water temperature from 44 degree to 41 degree, what is happening? You are increasing the lift on the chiller. So when you are increasing the lift on the chiller, obviously chiller power consumption will be higher. So chiller power will go up. But what's the advantage? Just remember the previous slides when we say that the chiller efficiency is 10 times than the pump efficiency. So we need to work chiller more harder because we know that chiller is more efficient. So the delta of the power consumption will be less because it's more efficient. But obviously the chiller power will go up. Now see what is the cumulative effect. Now chiller was 464 kilowatt with low flow, it becomes 490 kilowatt. Chill water pump was 52 and now becomes 16. So overall, you see this is the effect which was savings on the only chill water side. Now people who want to optimize the operating cost or they are more focused on the operating cost, they can put some kind of more efficient chiller by putting some more money on the chiller and make it almost at par efficient even with 41 degree temperature. That is still possible. Or people who wants to focus on the first cost, they can keep it as it is because anyway still there is a savings. Now we will see what is the effect on the air side as well with the similar kind of approach. So typical supply air temperature for a design, what we practice is basically 55 degree Fahrenheit and the room set point we keep it around 75 degree Fahrenheit. So close to around 20 degree delta T. The interior zone supply air temperature also we keep it around 55 degree. Here interior zone means we want to mean those area which all the sides are already air conditioned. If your all sides are already air conditioned, you can get always a air conditioning, some effect of air conditioning of the adjacent wall because it will actually that temperature will flow and you will feel that cooling effect. So what normally you can do while optimizing your system design for the interior zone air handling units, you can little bit increase your supply air temperature because still you'll be able to give the same kind of comfort because your all other side is already air conditioned. Now let us discuss what is the effect of this low flow because you are earlier you are getting your temperature around 55 degree Fahrenheit. Now with Airside HU with high delta T chill water coil, you can get a supply air temperature between 45 to 48 degree. Because first of all, your chill water temperature is lower. Earlier it was 44, 45, now it is 41 degree. What you can do is that you can increase your set point of the room little bit higher. Still you can get the same kind of comfort level. Why? Because when you are sending lower temperature, your humidity level will be low. So as your humidity level will be low, obviously you can get that benefit. But on the prima facie, what is happening here, you are increasing the air side delta T from 20 degree to 30 degree or 32 degree. Now that benefit will be percolate to your fan sizing or the CFM of the HU. So it will lower your required airflow by 30 to 40%, still able to achieve the required capacity. This is a typical example with 55 degree Fahrenheit air handler option, supplier with air handler option, and 45 degree. I'll explain all these three cases. So basically 55 degree Fahrenheit, your CFM requirement becomes close to around 18,750. So your fan HP becomes 17.8 HP. With 45 degree, the CFM drastically comes down to 11,360. Now, as the CFM comes down, so what is practically happening? You are able to give a lower size HU, and at the same time, you are able to save that power consumption of the Airside, which is 12.8. Again, here you can further optimize how, because see, there would be different approach for different people, because somebody wants to optimize on the first cost, they would select the second option. Somebody would say that, okay, I'll put some more dollars into the first cost, and I'll have a further better operational cost. He can choose the second one, where you can further lower your fan discharge velocity or the coil phase velocity, and your power consumption can be further reduced on the air side. So this is basically the kind of savings which you can get from here. You can see that the savings almost 50%. If you choose the third options, your savings from the first option is almost 50%. So this is the kind of savings you can get on the operational cost. I'll show you a case study which is already done by us in Denver, Colorado, and this particular building was an office building. And this was the configuration actually. 500 TR chiller, 250 TR, each into two numbers, seven size, 40 HUs were there, one per floor. So this is basically the water side installed cost. Initially, it was designed with 10 degree Fahrenheit delta T, which has been changed to 18 degree Fahrenheit delta T, and this was a savings which has been brought. So obviously the labor cost will also go down, your pipe and fittings will also go down, the valve sizing will come down, insulation cost will also go down, definitely the pumping cost will go down, as well as cooling tower and electrical cost. Yes, you can see that there is some kind of pluses on the chiller part, because as you know that you have to put some money on the chiller to make it as efficient as it was with normal 10 degree Fahrenheit delta T. But this what, because we have already said that the chiller efficiency is the highest among all the component, so it is worth to work that efficient machine harder. Also see this remarkable cost savings on the first cost for this airside installation. So air handling unit, you have saved your labor cost, airside you have saved, sheet metal cost you have saved, electrical cost you have saved. So total savings was close to around $64,000. So now if you combine, it's close to around $121,000 in the total system cost which has been saved for this particular system. Now we have done an energy analysis. At the time of energy analysis, what we have found that there is, after saving this 121%, $121,000 in the first cost, still there is an energy savings of close to 4% with respect to the normal 10 degree delta T design, conventional design. So here the customer was more concerned about the capital cost. So that's why they have not invested anything on further on the capital cost to further gain on the energy. But our team did it and share a proposal where they have confirmed that if they would have invested another $50,000 on this system, their energy savings would have gone from 3.4% to close to around 12% to 13.5%. And at that time, they could still save $71,000 in the first cost with a 13% on operational savings. Another case study, because we have been only discussing about our the US origin. So we did the similar thing in one of the IT park in Mumbai, and this was the configuration: 1600 TR, 800 TR into 2 number centrifugal chillers. Daily operation hours was 16 hours. We did this the operating hour analysis. Similar thing. Initially, it was 12-degree delta T system, which we proposed to customer to make it around 14.4 degree delta T, from 12 to 14 degree. See the reduction on the flow rate of the pump, and also you can see the reduction in the flow rate of the condenser water pump. This is a 2 chiller configuration. So the chiller power consumption, yes, it has increased from 0.57 to 0.61, but because of this overall reduction, see the impact. So earlier the pump sizing was 1593 GPM with 10-inch pump size. With it has gone to 1180 GPM with 8-inch pump size. Your chiller pressure drop has gone down. Your pumping power gone down from 17.7 kilowatt to 59.6 kilowatt. Same is the effect in condenser circuit. We have increased the delta T. So pipe size from 12-inch to 10-inch. Your pump power from 81 kilowatt to 63 kilowatt. The cooling tower also, as I mentioned, the pipe size become less, the flow rate become less, your delta T increases, CT effectiveness increases, and your fan power gone down to 9.5 kilowatt from 11.8 kilowatt. We uses the similar concept on the air side as well, and this is the savings what we actually got on different HUs. Average was close to 22% power savings on the air handler power consumption. So considering 2 chiller operation, so this is the delta actually. If you see, obviously the chiller power has gone up, but see the power consumption of the total system. Net saving per hour is 56 kilowatt, which for a 800 TR chiller and which is running for maybe 365 days with 16 hours, it's a huge savings which comes. So this is what I thought to explain, and this is the design which we feel that we should start adopting, because it's already available in and practiced outside India more frequently rather than within India, because we still, though in few cases I agree, though in few cases we have seen that people are adopting for a high delta T design, but this is definitely beneficial, and all our consultants, system designer, as well as the chiller manufacturer like us should promote this, because ultimately this is beneficial for everyone. You can save first cost, you can save operational cost, and at the same time you can save your environment as well. So with this, basically I'll come to my last slide. So this is the conclusion and benefits. Convert to low flow design, and this is how you can get the benefit: lower running cost, lower capital investment, less space constraint, less electrical load. So you have all the benefit. Probably this is basically, you can say that it's a holy grail or ultimate I mean, look out for any kind of system designer or the chiller manufacturer, this kind of performance. Obviously this is the overall summary. This is the same thing which I was explaining, so it is presented in a uh, pictorial form so that you can understand and visualize better. With this, I'm ending this presentation. I have come to the end of the presentation. Anyone is having any question, you can free to ask.
Thank you, sir. That was a wonderful and detailed presentation that we just saw. It was very informative, I must say. So I'll request the audience members, if you have any questions, please put them in the chat box. We can take up the questions, or if you want to unmute yourself and speak, you can, but chat box is preferred. Do we have any question? Yes. So there is a first question. It appears that this is the best design approach. Could you please shed some light into why this was not adopted earlier? Is there any disadvantage? So can you take that question?
Yeah, right. Thank you for the question. So, see, basically, these things are continuously evolving, and people are always doing a lot of research and development to find out how you can save your uh, energy and as well as your first cost. The as you have rightly said that what is the bottleneck? See, the bottleneck is that earlier days the chillers were not very suitable to handle the high density kind of syndrome. So if your flow gets into lower stage, if your flow go lower, so in that case some of the chiller might have problem. But now we have come a long way. I mean, as I explained that we have come a long way, and every manufacturer has got chillers which can run with 1.5 gpm, even 1.2 gpm also. So those things can be definitely optimized, and this is the time to adopt this kind of system so that you can save both on the first cost as well as on the operational cost. I hope I am loud and clear and I have answered your question. If you are not satisfied, you can further uh, you know discuss that. Right. So disadvantage is absolutely the same thing as I explained, that with high density, some of the chiller may not be able to perform properly. So earlier days that was a challenge, and that's why this system was not adopted. But now that's not a problem. So now it is absolutely possible to do this kind of system design, and we have done it also. I have shown you a couple of live example as well. HU inlet temperature is possible to supply in India hot and humid. Is it possible? Yes, high delta T is possible, but what see every our India is having a hot and humid climate, and that is not the scenario everywhere. So every city has got a different approach. I mean, different weather condition. So suppose say Kolkata, we have a very hot and humid temperature. Similarly, if you go to Delhi, Delhi might be very hot and might be cold during winter, but the humidity is not very high. So this is basically a generic thing. You might be able to achieve a high delta T system in Kolkata with maybe around 12-degree delta T, which can be adopted in Delhi with 15-degree or 16-degree delta T. But definitely the approach of 10-degree delta T has gone a long way, and we have to move from there, and we have to see that what best is available. We can, while doing a system design, you can very well discuss with your cooling tower manufacturer and try to find out a solution that if we get into, instead of a 10-degree delta T, if I want to design this to a higher delta T, whether your cooling tower will perform and what is the kind of performance of the cooling tower, and then accordingly do the system design. And if you actually see the approach, we have not minimized the your approach temperature. We have kept the approach temperature same as 7-degree, and then we have asked for a high delta T system. So obviously with high humid temperature your wet bulb will be higher, so in that case your approach temperature 7-degree. Yes, right question. We perform. I mean, everyone has a software. We have Train has a software called Trace. Carrier also have a software called HAPS. So this kind of simulation is possible in those software, and we can see that what is possible and what is not. Okay, to your other question, HU inlet temperature is possible to supply 45°F. See, with 41° chill water temperature, if it is a centrifugal chiller and you continuously maintain a 41° chill water temperature, we have seen our HU models which can deliver 45° outlet temperature of coil, that is supply at temperature of coil temperature. With our HU, it is possible. The other HU manufacturer can also advise on that. But with 41° temperature, it is possible. If it is a screw chiller, you are not able to achieve 41°. If the temperature increases, that's why I have shown you a range between 45 to 48°. See, the purpose is not that 45 or 46 or 48. The purpose here is to increase the delta T. If you increase the delta T, your CFM would come down. So instead of 45, if you get 48 and even 50 also, or 48 also, and still you can increase it to 77° your room temperature. So your delta T increases to close to around 30° or 29°. Still you would get some kind of savings on the flow rate. So if you get a flow rate savings there, your fan size will also come down. And if your fan size come down, obviously the HU sizing will also go down. And at the same time, you can save a lot of power because your fan size is lesser. So that's the approach. Here we have given some example about certain temperature. So that is not sacrosanct. The temperature can vary. Here we are discussing about the concept which we should adopt.
Yeah. Thank you, sir. You have very religiously answered all the questions. So thank you very much for that. So I think we don't have any more questions here. So I'll request once again our programs chair, Mr. Amitabh Datto, to kindly deliver the vote of thanks. Okay,
Yeah.
sorry. Before that, Mr. Arvind has a question. Are you sure to maintain 41° C all the time? Because practically, it is very difficult. It's not 41°
41
C, it's 41°F. I think we're talking about.
41°F chill water temperature, 41°F chill water temperature is achievable. We have designed that system, and we have chiller to deliver that. So yes, it is possible. Bigger chiller, it is furthermore possible. Smaller chiller, might be here and there you face little difficulty. But as I mentioned that here the temperature is just not that sacrosanct, or there is no hard and fast rule that you have to fix it to 41. If you're comfortable in 42°, that is also sufficient, but you increase the delta T to 15° or 16° or 17°, so that you can get benefit of the flow rate. Old existing chiller can be retrofit, that you need to see, because if a chiller is designed for a 10° delta T, probably that particular manufacturer have a software and he can select and say that whether that same chiller can be operated at a high delta T syndrome. Might be possible that I mean, you need to change a model to achieve it. That might be possible, because old existing chiller might be designed with a 10° delta T, and it's all heat exchangers are designed according to that. So probably you need to see whether it is possible, and you have to contact that particular manufacturer. Which insulation materials is good for chill water line insulation?
But we're not talking about insulation materials here.
Yeah. Okay. So I think the other member in history are more knowledgeable than me to answer your question regarding insulation. But I think closed cell nitrile rubbers are good at the time being. I mean, obviously we have leave away with this thermocol section and all. We have stopped using it, or we have reduced usage of that. Closed cell nitrile rubbers are good. I think people are also using some of the cases uh, P insulation, which is also giving good performance. But anyway, I'm not an expert of insulation, so I'm nobody to answer that. Yeah, closed cell nitride rubber.
Yeah. So if participants want to know more about insulation or other topics on this HVAC field, so you can go to our YouTube channel, and there are a lot of recordings that we have put there of various technical talks. So you can find some technical talk on insulation also, and it might help. So yeah, that's all. I think there are no more questions. So we'll wait for another 10-15 seconds, and then we'll yes, yeah, we'll upload this video also in YouTube. By tomorrow, you'll be getting this video in our YouTube channel, Ishre Kolkata Chapter's YouTube channel.
And to all the audience and participant, I have already displayed my number and email ID. So if you have any kind
Yes.
of further queries, you can directly reach out to me. I'll be happy to answer your queries.
So can you put your phone
Yeah,
number
sure.
and your email ID in the chat box? Or display is fine. Yeah, I think display is fine.
Shubham, there is one question from Digvijay. Again, it is about insulation thickness.
Insulation, yeah. Before that, Mr. Anand has put a question. Do we need special kind of control valves for high delta T?
Just a moment. I'm not able to
Yes, yes.
see. Yeah, obviously, I mean, all the control valves and all the valves, I mean, not only the control valves, any valves needs to be selected based on the revised flow rate, because when you are using a high delta T, you are reducing the flow rate, as we have mentioned that. So obviously, conventional valves with conventional flow rate, obviously your control valve, if you change the flow rate, your selection of control valves will also change. So obviously, with high delta T, control valve selection will also change.
Yes, and about calculating the chiller insulation thickness, I think you might have to refer to um, other
Yeah,
materials
so,
that are
Insulation
available.
Mr.
methods.
And
Digvijay, I mean, see, I can tell you the concept. So there is formula also which is available. I mean, see, what you have to see that with what insulation thickness you're practically you are protecting the condensation. So you have to see that where your dew point is getting achieved, so that the condensation doesn't happen. So your thickness should be higher than that. So that's the concept actually. Normally this chiller thickness is basically guided by our factory, and from the software itself we get it, that what kind of thickness is acceptable. But if you actually want to calculate, so basically you have to go into the depth of psychometry and calculate that, at what thickness this is not actually achieving the dew point temperature, so that the condensation can be restricted.
okay.
Okay.
Um, sorry about mistake.
Mr. Arvind Kumar, sorry, I am, you need to change your all valves. Yes, you need to change your all valves. See, when you are retrofitting, when you are practically retrofitting it, if you see the actual presentation, what we have seen, that it will downsize your piping also. So if you downsize your piping, obviously once the pipe size change, accordingly your valve size will also change. So you have to reselect all the valves and pipeline for this high delta T system. If you use this high delta T system in your existing pipeline, that probably will not help, because then the purpose will be get defeated.
Yeah.
Yeah. Okay.
Thank you, sir. So now, Amitabh, if you can kindly deliver the vote of thanks.
Thank you, Shubham. Thank you very much. Uh, Again, a very good evening we are spending with Mr. Supratim Mukherjee with lot of detailed technical discussion. I believe all the participants get some good knowledge, and if any requirement for further knowledge, they can directly contact with Mr. Supratim Mukherjee. Thank you, Mr. Mukherjee. Thank you very much. Within a short notice, you agreed to deliver such kind of technical presentation, completely technical presentation. So we are very much thankful to you. Thanks for the audience who are joining today, and we are looking up for the some more technical sessions in coming future. And on 15th of September, we have another technical presentation at Hotel Altair Boutique Hotel at Sector 5. Shubham, can you please share the flyer for that particular project, the particular
I'll try
program?
to say, yeah, yes, yes. Just give
Uh,
me a moment. I'll try to share.
so we are expecting some audience on that particular date also on 15th September, 6:30 p.m. onwards at Altair Boutique Hotel, Sector 5.
Sorry, just here it is.
Yeah.
So we'll be celebrating Engineers Day on that day. So all our members are invited to that program.
And again, requesting all the participants who are here to join ISRE, request to them, please join ISRE so that you can also get more technical knowledge and we can share the knowledge. So that's all. Hope you
Yeah,
all
thank you.
enjoyed the session. Again, thank you very much, Mr. Mukherjee, and audience. Thank you, Shubham. Thank you, ISRE Kolkata chapter.
Thank
Thank
you
you.
very much.
Thank you all.
Thank you all.
Thank you, sir. Thank you. Bye. Have a good day. I'll close the meeting.